morning. My name is Dick Sam, the author of this report, Superconductivity, the Structure Scale of the Universe, which is archived at the National Laboratory. It's been there for 18, 19 years, and I've got upgraded over the years many times, but I thought it would be important that I try to express some of the ideas there in a more visual manner to make them a little bit more understanding and provide the context in which they were developed. And the context is essentially a very broad, what is the universe made of? Now, if you look at the current literature and you ask astrophysicists, physicists, and they'll be very blunt in telling you that we really don't know what the universe is made of. But we know that it's there's measurements that indicate that it's largely 74% dark energy, 24% dark matter, but we only see 4% of the normal matter, the stars, the galaxies, the light-emitting objects out there in space. Also, in the context of this, we have the phenomenon of superconductivity, which people really don't understand how it works, but the phenomenon is that a material going below a particular critical temperature obtains this characteristic of the current flowing without resistance. I try to bring this concept into chipping away at, what the universe is made of. I try to put it also in the context of steric forms, triangular forms, basic geometry. It looks a little complex here, but basically we have two steric forms that are mirror images of each other, and having the characteristic that when they put together they form this lattice that is that fills space, which I think is a necessary characteristic. And also they fill space in such a manner that they maintain what's required in terms of elastic condition, the conservation of energy and momentum, concepts that have been established over the last few hundred years. But I take this in the context that I don't really say that we're going to develop a theory of everything that I can deterministically say by delving into this, that at the end we're going to have equation such and such, that theory of everything. And I say this in the context of the discussion of these two gentlemen as they strolled the Princeton campus in the 1950s. Albert Einstein and Kurt Gödel. Einstein had the concept that the world was, or the universe was, totally comprehensible by writing down a particular set of equations. You could deterministically establish the universe. Gödel, through a brilliant mathematician, took the view that this was impossible. He, through his incompleteness theorem, had proven to his satisfaction that if you set up a series or a set of axioms that defined a particular physical phenomenon, that was all right within, the box that these axioms were valid. But if you went outside the box, the approach was not valid. So, in that sense, you could never define the universe in some kind of mathematical sense. In my view, they're both correct. I mean, it's like the world is comprehensible and the world is incomprehensible. This brings up the general question of why is the universe so stable? I know all around us we have tremendous activity. I mean, me just moving here, the life itself that I have in me and you, We have airplanes going through the air, ships moving through the water, the Earth rotating, wave action, tidal action between the moon and the Earth, stars going through their dynamic situation, birth and growing old and decay, neutron stars, quasars. But in essence, the universe, I'd say 99% plus of the universe is stable. It hasn't changed since the beginning, in the supposedly at the Big Bang. Atoms such as hydrogen, formed at that time, still exist in our body at this time, 13 billion years later, in still the same form. They haven't changed. Even the atoms that have, through some type of nucleosynthetic event, have progressed, transformed into carbon or the higher elements in a periodic chart. Once they make that transformation, say 9 billion years ago, 5 billion years ago, they maintain that state through the present and into the future. And now I'm going to kind of address that problem. I'm going to introduce some historical figures. And the first one, of course, is Isaac Newton. He had his second law of, most prominent second law that indicated the force is equal to the change in momentum per time. But he didn't have that idea of what energy was. I guess he thought about it, but it was up to across the channel in France, this woman, Noether de Chatelet, she did some experiments dropping the balls into clay and measuring the deformation, and knew that determined that energy is related to the velocity squared, not to v. That was the question: was energy related to just the velocity? No, it was related to velocity squared. So that introduced the idea of what is this when energy and momentum are conserved. They brought up that question. Later, Maxwell, that velocity, he was based upon the experimental data at the time collected by his prior compatriot Faraday, and based upon the experimental data, the epsilon, the permittivity, mu, the permeability is measured in coils of experiments, coils of wire in different configurations, and by taking those two particular experimental constants, square root, reciprocal, and came up with this velocity c, which is the speed of light, which he indicated that was how electromagnetic waves were transmitted in space. And then this idea of kinetic energy, Boltzmann introduced the idea that this energy is related to temperature through his Boltzmann constant, in indicating that even at the gaseous scale, the kinetic theory of gases, gases, entity, molecules, atoms that compose these gases moved with a particular velocity, which could be described as their kinetic energy, mv squared. And then later on, in his 1905 papers, Einstein related that c to energy itself related to its mass, to an entity's mass. Energy and mass were related through this velocity of light squared. And then, of course, he went on with a few more gray hairs to develop his general theory of relativity, in which the curvature of space, mass itself, lended to the curvature of space. And then parallel to this, Max Planck developed the idea of the quantum, that energy somehow was quantized into, let's say 2 pi over time, which is a frequency. And this was somewhat counter to Einstein's view, because Einstein, with his field curvature concept, assumed a continuity, and whereas this Planck concept was essentially a discontinuity. And Einstein, to his dying day, didn't really thought this was kind of a incomplete view of the universe. Somehow his continuity view would overcome, and that kind of goes back to his idea how the universe was deterministic, when essentially it was not deterministic, as reflected in this concept by Max Planck. And then de Broglie came along in the 1920s with this idea of momentum matter wave. Matter itself could be reflected in a wave form at the Planck scale, and with a characteristic dimension b in this case. And then at that same time, the German scientist Werner Heisenberg showed a limit to all of this at what he called the uncertainty, where there was a point beyond which you really could not measure, as defined by the Planck constant divided by 2, momentum times a distance, momentum m delta v, distance delta b, or energy delta energy or delta time. Those products could not be defined within certain limits. And then you have the idea of quantum mechanics, which is developed in the same context, in the same time period. Niels Bohr, Edwin Schrödinger, that you could actually develop a wave equation, a solution to the wave equation in terms of an energy form. And a little bit prior to this, I guess in the 1910s or early 1920s, Emmy Noether really contributed to the development of these concepts in terms of her idea of the translation of time is energy, the translation of distance is momentum. There are many other transformations, but as far as our discussion, I would like to stick to these 2. And then, of course, in the 1920s, you had the idea of the Big Bang, the beginning. The priest, Monsignor Lemaitre, using Einstein's field equations, essentially said that it could be interpreted as having a direction, a beginning, and then proceeding towards some kind of expanding universe, which is expanding into the future. And Einstein was notably didn't like this. He at the time, he thought of the universe as in a steady state, that it did not change with time. And he told Maitre, your mathematics is beautiful, but your physics is disastrous. Anyway, a couple of years later, Hubble, on the other side, towards the bottom, experimentally measured this expansion of the universe, and it was named in terms of his Hubble constant. There was a changing velocity of celestial objects with distance, essentially indicating the universe is expanding. So how do we address this? I would start with many ways, but I'm saying I'd like to address it in terms of temperature. defining a scale, which Lord Kelvin had defined the temperature scale, and it had a temperature at the top, but then at the bottom you had 0. And from the previous presentation here, or these scientists, you can see that by uncertainty, there never can be a measurement of temperature equal 0. By the laws of thermodynamics, you can approach 0. You can have extremely low temperatures. You know, you can have 0.000, infinite number, almost infinite number of zeros, almost in a finite number of zeros, but you can never approach, or you can never reach 0. And in this context, and in the context of what I've done before in terms of these scientist presentations, I'd say that there is I wouldn't say a new temperature range, but it defines a temperature range where there's a top, a middle, and a bottom. The bottom defined by the Heisenberg uncertainty, matter waves, and the top defined by c squared. And it all goes back to this Maxwell, his formulation or interpretation of Faraday, these two constants, epsilon and mu, and the derivation, reciprocal, inverse, square, establishment of C. Essentially, what I'm saying is that the permeability, epsilon, or permittivity, epsilon, and permeability, mu, define states. You can't really define a system by one without the other. And in that term, these epsilons, they can be greater than 1 or less than 1. But they're limited by the fact that you cannot go faster than the speed of light. You think of it in terms of group velocity. If you have a group velocity, you have a phase velocity. The phase velocity can be greater than the speed of light, but at a certain point they reverse themselves, and the phase velocity becomes the group velocity, and the group velocity becomes the phase velocity. And it happens that if you take into consideration the uncertainty principle and the matter waves, this transition takes place at the nuclear diameter. Below the nuclear diameter, the phase velocity becomes the group velocity becomes the phase velocity by the particular transformation that is shown there. So the problem is that, again, back to the origin of my presentation, these triangular forms, which I hope to kind of explain a lot of this. What shape do you use? Traditionally, you have the Platonic solids, which of course goes back to Plato a couple thousand years ago, and none of them really fill space except for the cube. It was once thought that the tetrahedron would fill space, but if you take tetrahedrons, and I've done this myself, you put them together, and all of a sudden your lattice becomes distorted, and in order to proceed, you have to break bonds, and you create voids. And this has something to do with it is analogous to ping pong balls in a box. You throw ping pong balls into a box, you can fill the box with ping pong balls, but there's always voids there. So the cube is the only one that fills space, but it doesn't provide the symmetry that I was looking for. And that's why I go to this particular triangular shape. I call it trisine, but they're triangular forms which when put together, as I discussed in terms of the plate separator, the oil water plate separator, they fill space. And they fill space in a particular way. The dimensions have, if the dimensions are of this triangular form are defined in a particular way, the conservation of energy and momentum are maintained, which is very important. So you're going to construct this lattice, you're going to define it in terms of an elastic condition that defines this stability of the universe and superconductivity. That would be one characteristic that this lattice would have to have, is they would have to fill space with this property that of elastic or something that resonates, that essentially is not diminishing with time. So in the context of what Heisenberg and all these scientists say, these are relationships that must exist for this lattice to have these properties. And if you work and then what mass? Okay, it has that establishes the dimensions of this lattice. But then, what is the mass? And the best that I can come up with is it's something maybe related to what Steve Weinberg came up in 1982. It's a mass actually related to the Hubble constant, the gravity constant, these fundamental constants, and Planck constant, and the speed of light, and it's a mass that's 1 times 10 to the e to the 10 to the minus 25th gram, which is about 110 times the mass of electron. So that's the mass that has to exist in this lattice to give it this elastic property. And this in the geometry of the lattice must be that it has internal dimensions a over b over 1 over 2.3791, which I've calculated with Mathematica to be true. So that goes back to this original diagram of the lattice, the required lattice to maintain that conservation of energy and momentum characteristics, so that it can be used as a vehicle or instrument for explaining some of these physical phenomena in the universe that seem to have a long-term or a constant or a stable characteristic, such as superconductivity, dark matter, dark energy, the stability of the nuclear atom, the forces within. And using these numbers to come up with these parameters for the standard model, material superconductivity, and the cosmic universe. Essentially saying that it goes back to those Maxwell relationships, that if these 3 conditions must exist in concert with each other, it's like it's a law of nature, so to speak, that if one exists, then the other 2 exist. At the cosmic level, this resonance or stability exists at an extremely low temperature, 8 times 10 to the minus 16th K. In the B dimension is about 22 centimeters, and the time oscillation is on the order of 8 hours or 29,000 seconds. And this is essentially saying that dark energy that exists out there, it has these dimensions it operates in a very stable manner. And this is how it fits into that overall model. The dark energy, it takes up this little sector of that overall model. And as I said before, it's a theory, it's a representation of what the dark energy is. It's extremely cold, but probably in concert with the dark matter, which is essentially at that same temperature. And only candidates for that type of thing is maybe cold hydrogen, probably a Bose-Einstein condensate that would exist at that temperature, not readily detectable by present electromagnetic means. Material superconductivity is at a different range. The B here is the dimension B is on the order of angstroms, and the time is extremely fast, 10 to the 10 to the minus 13 seconds, still maintaining that triangular resonant form. And this is the explanation for the superconducting phenomenon, where essentially that material there at that particular temperature has that particular lattice resonant elastic characteristic that allows it to go on in like a perpetual manner. And the concept of superconductivity is covered in this area here of that overall model. Again, saying if this exists, then the next tier and the next tier above that also exists. They exist in tandem with each other. Next, the satellite, the WMAP, the Wilkinson Microwave Anisotropic Probe, it is defunct now, but it's replaced by Planck, and we had the COBE before it, but it measured the cosmic microwave background radiation, which followed the Planck black body curve, and measured the temperature of the universe at 2.7 Kelvin, which is considerably above the what I said, the dark matter is at 10 to the minus 16th K, but it also fits in the overall model. It exists because the lower one exists, and here how it fits into that overall model. And now at nuclear conditions, the temperatures are extremely high, 10 to 13th Kelvin, and dimensions are in the order of the 10 to the minus 14 centimeter nuclear dimension, and but still remaining within that resonant that model. And here is they're called out, the particular parameters. Again, they exist in tandem with each other. Recognize that the other dimensional characteristics or representations of this phenomena also exist. And it's interesting to note that the weak force and the strong force can also be characterized in these terms, in that the weak force is, you would think that because it's higher in their relationship there than the strong force, that shouldn't be, but it is that way, because now you're talking back in the again, where the group velocity is replaced by the phase velocity replaced by the group velocity, and we're looking like on the other side of a mirror. We're we're observing on this side, but we're interpreting what's going on over here, and still it reflects the basic overall phenomenon that if this exists and that exists, and that, it all hangs together. And then we have the Majorana condition. That's the top row in terms of the c squared. And again, this is called out here. This condition exists in tandem with the others. So this is kind of the overall model. Also, in parallel, it's always asked the question, well, how does gravity fit into this? And going back to Einstein's curvature, mass bending space into a curvature, his tensor relationships, and I was able to essentially make the same identity that this mass of the universe, the curvature of the universe actually can be extended back through his constant g over c to the fourth in terms of the actual geometry that we've been talking about. The only problem is that this g must change. It's a changing g. Now this is a problem. I know that observationally we do not see a changing g with back to the Big Bang. Apparently the measurements indicate that the g does not change, but somehow I think that it from a different perspective, which I don't know as of yet, but it does change. It changes in terms of well, I know that it has to change to make this relationship work. So that, I can't go beyond that. It's like it has to change in order to make this relationship work. What other factor is involved so that it is apparently unchanging? I don't know at this time. Maybe in the future it'll be apparent. Anyway, this currently this mass 1 times 10 to the minus 25th gram. There's the Fermi satellite is up there spinning around for the last few years, launched in 2008. It should be able to measure whether that is a property of space or not. And to date, the Fermi satellite has it has measured a particular characteristic that maybe indicate that a lot of space is radiating as though it were from the subnuclear dimension. It is from this reflective dimension. I measure this. I interpret this as the negative slope of the gamma ray that have been measured by Fermi. As I mentioned, this is a speculative whether this negative 1/3 slope of the gamma ray radiation is measured by Fermi is a measure of this reflective subnuclear properties of space. That is yet to be determined, but we're still looking. It's new. Another experiment that was done was the gravity probe B, which is now defunct, but the data indicates that Einstein's theory of relativity is verified, and that was the purpose of this experiment, to verify Einstein's theory. But in conjunction with that, I was able to interpret some of the data in a little bit different manner. On board that satellite were 4 gyroscopes, very sensitive, and with time they noted an oscillation in these gyroscopes, which they couldn't figure out how to identify and correct. But it was interesting to note that the data from these oscillations conform to the oscillation that I had calculated, 29,600 second or 8.2 hours. They seem to actually be measuring that oscillation and the harmonics thereof. And that's in my paper. Haven't really got too much feedback on that, but that would be interesting if that were really the case. Okay, at this point I would just like to leave the rest of the presentation with this moving, say, animation of this triangular form. Again, it's a triangular form that oscillates between one steric form to the other, three-dimensional lattice. This is a small increment of it, but my theory or hypothesis is that it extends throughout space. I have a criticism that, well, it, it's unstable. It's unstable. That's the basic. It's unstable, and I counter that with the idea. Yes, it is unstable, and I think that it really only exists if there are boundary conditions to it. If there are it exists in a boundary condition, essentially, if it exists in the nuclear stage, because you have the boundary conditions of the nuclear diameter, which is defined by the speed of light. That boundary condition, what's above and below that, and the superconductivity is defined by the boundary conditions that are in a material, defined in a material. The boundary conditions are the physical limitations of that material. Form a boundary condition in which that superconducting triangle matrix can form and be stable. The cosmic condition is stable because there are boundary conditions to the universe. And unknown, I have to say that, what are the boundary conditions of the universe, but I tend to think that there are existing boundary conditions such that dark energy defined by these triangular form, they're oscillating at the extremely low frequencies, they do exist, and very difficult to measure, but maybe sometime in the future somebody will be able to measure. I've tried to, like with the gravity probe B and this Fermi data, there's indications that they do exist. The oscillation of some stars, the RC stars seem to oscillate in that time frame. So the future is open to whether this is right or wrong. It could be extremely wrong. But anyway, we wait. Thank you very much.